Welcome to our comprehensive deep dive into the control environment for artificial intelligence. In this session, we will explore the massive ecosystem of safeguards required to build, use, and eventually retire intelligent technologies safely. We are going to unpack 6 major categories of protection, ranging from executive boardrooms and strict technical firewalls to legal compliance and human ethics. Understanding this interconnected web of controls is a massive advantage in the real world. You can use this exact knowledge to build a unified risk checklist the next time your company wants to buy an automated resume screener or a predictive sales tool. You will know exactly how to verify if the vendor is protecting your company data, adhering to privacy laws, and producing fair, unbiased results before you ever sign a contract. Before we look at the specific categories, we must clearly define the role of an auditor in this environment. The golden rule is that an auditor validates controls, but they do not execute them. Think of a safety inspector at a theme park. The inspector does not personally climb the roller coaster to tighten the bolts. Instead, the inspector reviews the maintenance logs to prove that the mechanics tightened those bolts according to the official safety standards. Similarly, you will not personally run the software scripts that detect unfair bias in an algorithm. You will gather evidence proving that the engineering team ran those tools, correctly interpreted the results, and met your company requirements. Furthermore, you do not need to reinvent the wheel. Many existing cybersecurity and privacy protocols simply need to be expanded to cover these new technological concerns, combining policies, technical tweaks, and continuous monitoring to prevent disaster. Our first category is governance and organizational controls. This is the foundation that dictates how a company manages its technological assets from the very top. It all starts with absolute accountability. A company must document exactly who is responsible for what. One way to do this is by creating a RACI chart. RACI is an acronym that stands for Responsible, Accountable, Consulted, and Informed. It is simply a matrix that maps out which employee does the work, who holds ultimate ownership, who needs to provide input, and who merely needs to be kept in the loop. To lead this effort, organizations should appoint a high-level executive, such as a chief data officer or a chief artificial intelligence officer, to act as the ultimate point of authority. Next, the enterprise needs a dedicated internal policy. This document establishes the core principles, incorporating legal regulations and risk management processes, ensuring the technology aligns with the overarching mission of the business. Organizations should also adopt established industry frameworks to provide a structured baseline for oversight rather than guessing what to protect. Asset management is another mandatory governance control. This involves creating an exhaustive registry of every single automated model in the company. Just as a logistics company tracks every delivery truck in a central database, a business must log every algorithm, detailing its purpose, the stakeholders involved, its current version, and its life cycle stage. Risk management at this top level requires a dedicated committee. This committee tracks key risk indicators. A key risk indicator is a specific metric that acts as an early warning signal, much like the check engine light on a car dashboard. The committee also reviews independent assessments from internal and external auditors and closely monitors the risks introduced by third-party vendors. Finally, governance includes tight control over legal contracts and agreements. For example, a company might now need specific contractual language to guarantee that a vendor has secured explicit legal consent to use certain customer data for training purposes, an obligation that simply did not exist a few years ago. The second category covers technical, security, and privacy controls. These are the concrete, operational safeguards built directly into the digital infrastructure. Data quality is arguably the most important technical control because intelligent models learn exclusively from the information they consume. Think of a municipal water treatment plant. If the plant takes in heavily contaminated river water, the purification system has to work incredibly hard to make it safe. Organizations must formally document the thresholds for acceptable information, the rules for resolving poor quality inputs, and the methods for continuous monitoring. Access controls must also be updated. Access for privileged administrators, regular users, applications, and third parties must be strictly calibrated based on data sensitivity. Strong measures like multi-factor authentication are mandatory. Furthermore, access cannot be granted forever. Companies must implement recertification, which is the process of periodically reviewing user accounts to ensure people only retain access to what they currently need for their jobs. Configuration management is the practice of maintaining systems in a desired, secure state. Modern environments rely heavily on automation to securely configure components, deploy software patches, and detect vulnerabilities proactively. By tightly integrating this with incident management, an organization can spot and fix a weakness before a malicious hacker can exploit it. Technical controls also demand rigorous testing frameworks. Teams must conduct end-to-end testing of the entire workflow, scenario analysis to see how the system handles bizarre or unexpected situations, and aggressive testing for unfair bias. Privacy and overarching data management require a massive suite of technical tools. This includes securing communication pathways and utilizing encryption. It involves hashing, which is a mathematical process that scrambles data into an unreadable string of characters to protect passwords. It also involves anonymization, stripping away personal details so individuals cannot be identified from a dataset. Teams must manage cryptographic keys, conduct regular privacy impact assessments, and enforce data minimization. Data minimization simply means collecting only the exact information necessary for a specific task and nothing more, much like packing only a weekend bag for a 2-day trip instead of bringing your entire wardrobe. Robust architecture, automated backups, and integrity monitoring are vital to keep the data safe. Lastly in this section is incident management. When things go wrong, the focus is on handling data breaches and operational interference. The auditor must review the overarching incident response plan to ensure that automated products are explicitly covered, with clear steps to identify the problem, contain the damage, mitigate the impact, and restore normal operations. Our third category is operation and lifecycle management. This focuses on the day-to-day running and maintenance of the system over its entire lifespan. It relies heavily on extensive documentation. Teams must create dataflow diagrams, capturing logical, physical, and context views of how information travels. Process flows break down complex activities like how data is collected, enriched, and outputted. Think of these diagrams like the plumbing blueprints of a skyscraper, showing exactly where water enters the building, where it is heated, and where it exits. Decision-making documentation is crucial for a concept called explainability. Explainability is the capacity to understand the exact techniques and mathematical scores a system uses to turn an input into a specific output. Documentation must cover the step-by-step logic, help end users understand the results, detail the underlying architecture, and communicate ethical compliance. Traceability logs must also record where information was sourced, how consent was obtained, and how the data was transformed along the way. Lifecycle management involves strict change management and version control. Any updates to the code must go through a documented approval process. Teams must assess the potential impact of a change before applying it, retaining formal records in a ticketing system. Modern environments utilize automated tools and containerization to manage these versions. Containerization is the process of packaging a piece of software with all its necessary files into a single digital box, so it runs flawlessly on any computer, much like packing all the ingredients for a meal into a single meal prep container. Even after a successful deployment, continuous monitoring must remain active. One major thing they monitor for is model drift. Model drift happens when a system loses its accuracy over time because the real-world environment it operates in has changed. Imagine a system trained to predict fashion trends based on data from the 1990s. If you use it today, the predictions will be entirely wrong because society drifted away from those styles. Category 4 explores the system development lifecycle, commonly known as SDLC controls. These govern the actual creation and building phases of the technology. The exact controls depend heavily on the project management approach. A rapid, continuous delivery approach like DevSecOps will handle controls very differently than a highly structured, sequential waterfall approach. Interestingly, many of these highly ambitious development projects never actually make it to deployment. This failure rate is rarely due to the methodology. Most projects fail because of poor leadership or completely unclear business requirements. During the ideation phase, teams must clearly document the problem they are trying to solve, align their objectives with broader strategic goals, and preemptively brainstorm any potential harm the system might cause. In the design phase, the focus shifts to technical architecture and data fitness. Teams must ask critical questions. Did we purchase this data legally? Is it complete? Does it accurately represent the diverse population it will serve to avoid unfair outcomes? Specific model types and system requirements must be strictly defined here. When it is time for deployment management, organizations often rely on automation to release the final software packages. If code is promoted automatically to live environments, auditors must verify that operations teams are closely monitoring these automated pathways for any unexpected errors. Our fifth category encompasses legal, risk, compliance, and regulatory controls. This is how an organization ensures it is playing by the rules of society and the law. Risk and impact assessments must be conducted systematically. Systems must be categorized by their danger level to ensure high-risk platforms are managed according to laws like the European Union AI Act or specific city mandates like New York City, Local Law 100/44, which regulates automated employment decisions. Because these technologies are dynamic, these risk assessments cannot be a one-time event. They must be iterative and constantly updated. For the highest risk systems, organizations must perform a fundamental rights impact assessment, often abbreviated as FRIA. A high-risk system is one that profoundly affects human safety or basic rights. This includes technologies used for biometric identification, managing critical infrastructure, granting access to essential public services, law enforcement, and border control. Think of a FRIA like an environmental impact study conducted before a corporation builds a massive dam, but instead of protecting the local wildlife, it protects human civil liberties. Alongside this, a Data Protection Impact Assessment, or DPIA, is required specifically to evaluate privacy threats. Compliance means adhering to all global, national, and local laws. Contract management ensures external vendors also meet these stringent legal obligations. A crucial control in this category is the whistleblower process. An organization must establish a safe, formal, and protected mechanism that encourages individuals to self-report unethical behavior, illegal activities, or potential societal harm caused by the technology without fear of retaliation. Finally, regulatory reporting ensures that specialized compliance mandates are communicated from the oversight committees and integrated into the daily operations of the business, sometimes taking the form of a voluntary code of practice. Our final category is ethical and human values. These controls ensure the technology treats people with dignity, fairness, and respect. It starts with an ethical impact assessment. Companies can leverage free, open-source guidelines or align with established corporate frameworks to embed responsible concepts directly into their development pipelines. Consent management gives power back to the user. Controls must validate that people are given the right to opt out of automated processing. Auditors review procedures ensuring the consent status of training data is respected, verify data retention limits, and confirm the organization can execute the right to be forgotten. The right to be forgotten means a company has a process to completely, permanently erase a person from their digital records upon request. Bias management requires constant vigilance. Testing must look for bias introduced by the human developers themselves, as well as testing outcomes against protected characteristics to prevent inequality. Validating representative sampling procedures helps detect failures in the training data. For example, imagine a medical diagnostic algorithm trained exclusively on data from hospitals in a freezing, high-altitude mountain region. If that system is deployed globally, it might completely fail to diagnose diseases common in tropical, sea-level climates because its training sample did not represent the whole world. Transparency and explainability require organizations to disclose when people are interacting with an automated agent. To achieve true explainability, developers use specialized mathematical tools. One tool is LIME, which stands for Local Interpretable Model Agnostic Explanations. Lime isolates and explains why one single, specific prediction was made. It is like asking a teacher to explain exactly why you lost points on one specific essay question. Another tool is SHAP, or Shapley Additive Explanations. SHAP provides a broader view, showing the overall importance and weight of different features across all predictions. It is like looking at the syllabus rubric for the entire semester, seeing that homework is worth 20% and the final exam is worth 80%. For simpler setups, auditors can review rule-based models which operate on straightforward, human-readable logic. Lastly, human oversight is non-negotiable. There must be processes keeping humans in the loop to review outputs and conduct independent ethical reviews. Most importantly, anyone impacted by an automated decision must have a clear, functional appeal process to have their case reviewed by a real human being. To wrap things up, we have thoroughly explored the 6 domains of controls required for a healthy technological ecosystem. We covered top-down organizational governance, deep technical privacy protocols, the daily maintenance of operations, the structured phases of system development, strict adherence to legal mandates, and the paramount importance of human ethics. Remember, no single department owns all these responsibilities. The true value of an audit is validating that these diverse, overlapping controls are actually functioning together in harmony to mitigate risk. To solidify your understanding of these vital control frameworks, all the important topics and concepts from this session are covered in the multiple choice questions on rucloud.com. We highly recommend that you solve the chapter-wise questions to reinforce your learning before moving on to the next session. Thank you for joining this deep dive, and I will see you in the next episode.